me start with a quick recapitulation of what I said about solving for stationary states of the one-dimensional harmonic oscillator, just the salient features, before I move on to another topic today, which is a particle of mass m subject to a square well potential. That's also a one-dimensional problem. So really I'll be looking at the one-dimensional square well potential. But before we go on to that, let me recall for you the essential features of solving a differential equation, the time-independent Schrodinger equation, in the case of the harmonic oscillator, which we have already done. You will recall that the equation for the oscillator was of this form. This is the potential term, half m omega squared x squared. There is a psi on which it acts, and there is an E psi. Psi is a function of x. Then we defined certain variables. We defined the following. We wrote it in the fashion d2 psi by dx squared plus m squared omega squared by h cross squared with a minus sign because of the overall minus in d2 psi by dx squared is equal to minus 2me by h cross squared psi. And then we said that there is an object of dimensions of inverse length here. In my notation, alpha was root of m omega by h cross. Now that's an object of the dimensions of inverse length, which I have made using the constants that are available here, m, omega and h cross, given to me in the problem. Then we defined rho, which was alpha x, and which was therefore a dimensionless quantity. Recast this equation in terms of d2 psi by d rho squared plus so on, where psi was a function of rho. And in the process also got a quantity 2me by h cross squared alpha squared. Now this can be written as E by h cross omega, and therefore that's a dimensionless variable. In other words, what we are doing is the following. E will be written in terms of h cross omega, 1 h cross omega, 2 h cross omega, and in this problem n plus half h cross omega once E is quantized. So we got E sub n, where n takes values 0, 1, 2, etc., is n plus half h cross omega. So what is it that we have done? The message that it gives us is the following. Identify length scales, energy scales in the problem. Find out the energy eigenvalues in the problem in terms of that energy scale, in units of h cross omega. The reason why I had a length scale in the problem was, in this case, to go to dimensionless variable. Rho is alpha x, and that object does not have dimensions. Now this is a matter to be remembered in all problems that we will solve. And therefore, with this recap, I will move on to the one-dimensional square well potential. Use some of the tricks that I have learned here, and you will see the similarities in solving problems of this kind. So here is a schematic sketch of my one-dimensional potential. So this is V of x versus x, except that this is the origin and my potential is negative in a certain region. It's a square well. This is x is equal to minus a, and that's x equals plus a. Since this is the origin, anything below is negative, let that height be v naught, And therefore, I have for you, let me use another chalk, a potential of this kind. Of this kind. So you see, if you can see the difference between the white and the pink colors that I have used. V of x is 0 if x is greater than a, mod x is greater than a. So out there and out there, all the way to infinity, V of x is 0, and V of x is minus V naught, where V naught is positive. So it's minus V naught for mod x less than a. So this is the square well potential. 0 beyond a certain length scale and non-zero within that length scale. This is what I have. Notice that there is a natural length scale in this problem, a. So a is the width of the well, 2a if you wish, but a is typically the scale, the length scale, which determines the width in this problem. And therefore, I have a momentum scale in this problem. My momentum scale is h cross by a. This is the momentum scale in this problem. There is a nice interpretation. If the particle of mass m were inside this potential well, and you don't know where it is, roughly there is an uncertainty in its position, which is given by a, roughly by a, and therefore there is a corresponding uncertainty in its momentum, linear momentum, given by h cross by a. Then an energy scale naturally emerges in this problem. So I have an energy which is given by p squared by 2m, which is h cross squared by 2ma squared. Now this object has the dimensions of energy. This is clearly not going to be the energy of the particle. I am saying that this is an energy scale. In other words, analogous to the harmonic oscillator problem, where h cross omega gave me the energy scale in terms of parameters that are already available in the problem, and then when I quantize the system, I wrote the energy in terms of h cross omega, in units of h cross omega, as n plus half h cross omega in the case of the oscillator. Now here too, I will find energy in units of h cross squared by 2ma squared. To begin with, I can talk of the strength of the potential. So if I call this object h cross squared by 2ma squared as delta, my potential is V naught. V naught by delta has no dimensions, and V naught by delta will tell me the strength of the potential. In other words, I can tell you that V naught is 5 delta, 7 delta, 70 delta, 2.5 delta, whatever. But delta sets the energy scale in the problem. So typically in these problems, it's good to identify length scales, energy scales, and so on. Shortly, I will identify an object of the dimensions of length. But before that, I need to pass some comments to understand the classical picture. What happens to a classical particle subject to a potential like this? Now two things can happen. The total energy of the particle can be greater than 0. Although the potential energy, the potential is negative, you can see that, the total energy can be greater than 0 because the kinetic energy is overpoweringly positive. Now if the total energy is greater than 0, and you have to schematically show where the energy is, you would say that the energy is somewhere out there. if you think of this as total energy, then the energy level is above this axis, because this is the 0 of energy. In that case, the particle can move into all these regions. I will refer to this as region 1. Whatever happens inside the potential well as region 2, this whole thing is region 2, and this is region 3. So the particle can move anywhere it wants through region 1 all the way here, because the energy is greater than 0. However, you know that kinetic energy cannot be negative. So if the total energy of the classical particle is less than 0, suppose that happened, because the energy is somewhere out here, it is less than 0, then the particle is classically forbidden from moving into regions 1 or 3, cannot get from here outside the square well, for a very good reason, because if the total energy is less than 0, since the potential is 0 here in regions 1 and 3, the kinetic energy will be negative, because the kinetic energy is E minus V. And since V is 0 and E is negative, the kinetic energy is negative, and therefore 1 and 3 are classically forbidden regions if the energy, total energy, is less than 0. So let me just put down this point. There are therefore two cases, the total energy greater than 0 and the total energy less than 0. Now if E is less than 0, regions 1 and 3 are forbidden for the classical particle, which was initially inside the potential well, classical particle of mass m, because kinetic energy cannot be negative. Now if E is greater than 0, that is not true, as we have already seen, the particle can be anywhere. So there are two cases to discuss, E less than 0 and E greater than 0. If E is less than 0, since the particle is confined to within the square well, you say that the particle is bound by the potential, and therefore you have bound state solutions for the energy eigenfunctions with corresponding energy eigenvalues. So that is what we will look at immediately. We will look at the case energy less than 0. This is the bound state problem, and we will see how exactly the quantum situation differs from the classical situation. So let us first write down the equations to obtain the stationary state solutions. Now you will recall that the time dependence of a stationary state solution was given by some chi of t, which is e to the minus I E t by h cross, and if E were quantized, it would be E sub n t by h cross. The total wave function, of course, had a contribution from the space part, which was psi of x, and corresponding to the energy E sub n, you would have solution psi sub n of x for the stationary states, the eigenstates of the system, energy eigenstates of the system. The total wave function, of course, will be psi n of x chi of t, psi of x chi of t in general. So we are now supposed to solve for psi of x, analogous to what we did in the case of the simple harmonic oscillator, where we wrote h psi is equal to E psi. In that case, h was given by minus h cross squared by 2m d2 psi of x by dx squared plus half m omega squared x squared psi, that was h psi. You equated that to E psi. Now here there are three regions, two without a potential, the potential was 0, and the square well itself has a non-zero potential. And therefore, I have the following equations. In region 1, I have minus h cross squared by 2m d2 psi of x by dx squared, no potential, is E psi of x. The same equation holds in region 3 as well. Of course, it's obvious that it is good to make the equation look less clumsy, and therefore I can write d2 psi of x by dx squared is minus 2m e by h cross squared psi of x. Look at this object, minus 2m e by h cross squared. E is less than 0, and there is an overall negative sign. We are looking at bound state problems, and therefore minus 2m e by h cross squared is a positive quantity. Let me call that alpha squared. Now this object, what is the dimensions? This object, minus 2m e by h cross squared, dimensions, that's mass. This is m L squared t to the minus 2. H cross itself is m L squared t to the minus 1, the whole squared, because there's an h cross squared. And therefore, that gives me an m squared L squared t to the minus 2 by m squared L to the 4 t to the minus 2. And therefore, the dimensions here is 1 by L squared. Therefore, alpha has the dimensions of 1 by length. I'd like to keep alpha positive. So I choose alpha to be greater than 0, no loss of generality, and I say that alpha has dimensions 1 by length. That's a good thing to know. If you recall, this would be the analog of alpha in the case of the harmonic oscillator as well, except that the alpha there had a very different definition. It was root of m omega by h cross. And therefore, since this has dimensions of 1 by length, alpha a is a dimensionless quantity. That's a good thing to remember. I can now go back and write my equation very nicely. d2 psi of x by dx squared is alpha squared psi of x. So taking it to the other side, this is my equation for regions 1 and 3. That's what I have. Got to solve for this equation. The solution is simple. The allowed solutions are psi of x is some constant a, e to the alpha x. It's also true that there is another solution, e to the minus alpha x, apart from some constant b. But then boundary conditions have to be respected. Certainly at space infinity, that's x going to plus infinity or minus infinity, the wave function has to vanish in order to sustain the probabilistic interpretation. And therefore, since we are looking at region 1 first, in region 1 x goes to minus infinity and there is no problem here, whereas that blows up, and therefore in region 1 psi of x is a e to the alpha x. Now in region 3 psi of x is b, let's call that d, let's keep an order. Okay, b if you wish. Psi of x is b e to the minus alpha x, because when x goes to plus infinity this is fine and that is not. So I have solutions in region 1 and region 3. So let me write that here. Psi in region 1 is a e to the alpha x. Remember that alpha is positive. And in region 3 psi of x is b e to the minus alpha x. Now this is rather interesting. Of course, we have to check for consistencies. We have to solve for A and B, but if we do find solutions, which indeed we will, that tells us that psi star psi is not 0 in regions 1 and 3. That means that there is a non-zero probability of seeing the particle in regions 1 and 3. But these are classically forbidden regions. So this is a thing worth checking out. So the details of the calculation should tell us if indeed classically forbidden regions are accessible to a quantum mechanical particle. So that's a matter of interest in this problem. Now look at region 2. We are looking at E less than 0. In region 2, you have the equation minus h cross squared by 2m d2 psi of x by dx squared plus v psi of x is equal to E psi of x. But v is minus v naught, where v naught is greater than 0. And therefore, I have d2 psi by dx squared with a minus h cross squared by 2m outside is E plus v naught psi. So I write d2 psi by dx squared is minus 2m by h cross squared E plus v naught psi. I can always pull it to the side and write that d2 psi by dx squared plus 2m E plus v naught by h cross squared psi equals 0. I know that 2m E by h cross squared, I've already worked that out, has dimensions of 1 by length squared. So this also is energy, and this too has dimensions 1 by length squared. Here E is less than 0, v naught is positive, and 2m by h cross squared E plus v naught, if E is less than 0 and v naught is positive, so that's v naught, E is somewhere out here, so E plus v naught is anyway positive, and therefore this quantity I'll call it beta squared, where beta squared, like alpha squared, has dimensions of inverse length squared. I define beta to be greater than 0. So now I have two objects, alpha and beta, both positive by my definition without loss of generality, and the dimensions, natural dimensions, is inverse length for alpha and beta. I also have a delta which I have constructed with the constants that are available in the problem, and delta has dimensions of energy. Therefore, the depth of the potential V naught can be written in terms of delta, in units of delta, and lengths are scaled in units of 2m E by h cross squared or 2m E plus v naught by h cross squared in terms of alpha and beta. So I have this equation. Let me just rewrite that equation here. I have d2 psi by dx squared plus beta squared psi equals 0. Again, the solution to this equation is obvious. Psi of x, since we've already used a and b, let's say c and d, is c cos beta x plus d sine beta x. So this is a solution in general, where c and d are constants. We have to determine a, b, c, and d, which we will suitably. Now we come to boundary conditions. So this is the solution in region 2. So let me write that there. Psi in region 2 is c cos beta x plus d sine beta x. So this is what I have by way of solutions. But then you see there are boundary conditions, and the boundary conditions are such that the wave function is continuous at the boundary, and so is the first derivative. Now, how did I get that? So, a small digression as to how we get these boundary conditions at the boundaries, that is in this problem at x is equal to plus a and x is equal to minus a. Look at the Schrodinger equation. I h cross d psi by dt is minus h cross squared by 2m d2 psi by dx squared plus v psi. The wave function is continuous. That is our requirement. You need to take its first derivative and its second derivative. So, psi is continuous and vanishes at space infinity for the probabilistic interpretation. Therefore, d psi by dt is continuous, continuous function of x, that is what we are saying. So, the left hand side in this equation has a continuous function of x. Now, look at the right hand side. We assume that the potentials that we are considering has at most finite discontinuities. It's continuous or finite discontinuities. At some specific values of x. Now, if v of x has finite discontinuities, so does this. But this is a continuous function of x, the left hand side. And therefore, between the two terms in the right hand side, these discontinuities should cancel out, which means d2 psi by dx squared, the second derivative, has finite discontinuities. In order to cancel out these discontinuities in the potential v of x, that implies that d psi by dx is continuous. It is a continuous function of x. Now, that is the kind of situation we are facing here. It is obvious that that is not going to be the case in a problem where, say, v of x has an infinite discontinuity somewhere. And suppose this well at an infinite well. Suppose there was an infinite discontinuity in v of x, certainly the left hand side continues to be continuous, a continuous function of x, and therefore, the infinite discontinuity here must be compensated for by an infinite discontinuity there, which means the second derivative of psi has an infinite discontinuity or a set of infinite discontinuities. Now, that means that the first derivative d psi by dx has finite discontinuities. So, if v of x has an infinite discontinuity, d psi by dx has a finite discontinuity at that value of x. Now, in this problem, clearly we need to use the fact that d psi by dx is a continuous function of x. There are no discontinuities, which means I need to do the following thing. At x equals minus a, I have to match the wave function in region 1 with the wave function in region 2. I also have to match the first derivative of the wave function in region 1 with the first derivative of the wave function in region 2. Now, I have to do the same thing here. I have to match the wave functions between 2 and 3 and the corresponding first derivatives also at x equals plus a. So, at x equals minus a and plus a, such a matching has to happen. The wave function and the first derivative both have to be continuous. So, let me do that first. Now, in this case, I have the following conditions at the boundaries at x equals plus a and minus a. So, let us look at x equals minus a. Remember, we are working only with bound state solutions E less than 0. So, at x equals minus a, psi 1 is a e to the minus alpha a psi 2 is C cos beta A minus D sin beta A. This is what I have at x equals minus A. I have to match both of them. So A e to the minus alpha A is C cos beta A minus D sin beta A. So this is one equation that I have. Now look at the derivatives. At x equals minus A, the derivative there is alpha A e to the alpha x at x equals minus A. So I have alpha A e to the minus alpha A. This is for region 1. That means d psi by dx at x equals minus A. That's what I have. And then if you look at region 2, d psi by dx is given by minus c beta cos beta x plus d beta sin beta x minus c beta sin beta x plus d beta cos beta x, and you're substituting x equals minus A. So this is what I have. Now these two should be equated, and therefore I have alpha A e to the minus alpha A is C beta sin beta A plus d beta cos beta A. So this is my second equation. The first came out of matching the wave function. The second equation came out of matching the first derivatives at x equals minus A. I do the same thing for x equals plus A. So let's look at x equals plus A. Psi 2 is given by C cos beta A plus D sin beta A, and psi 3 is out there. So psi 3 is B e to the minus alpha A. So this is what I have. I need to match the two of them, and therefore my third equation would simply be B e to the minus alpha A is C cos beta A plus D sin beta A. So that's my third equation. Fourth equation comes out of matching the derivatives. So the derivative d psi 2 by dx at x equals plus A is what we want. So that is minus c beta sin beta A. That's the first term, plus d beta cos beta A. Whereas d psi 3 by dx at x equals plus A is minus alpha b e to the minus alpha A. So these have to be matched. So my fourth equation simply says minus alpha b e to the minus alpha A is minus c beta sin beta A plus d beta cos beta A. And that's my fourth equation. So these are the four equations. The upshot of the whole thing is this: I will have to work with these four equations and fix values for C, D, A and B, find solutions, and see if they are consistent. In fact, two types of solutions emerge. So let's look at this. I can add the first two equations. So that gives me A plus B e to the minus alpha A. So I am adding equation 1 and 3. So when I add it, I get 2c cos beta A. I'll call this equation 5. Right? I can subtract one from the other. So I have A minus B e to the minus alpha A. So I am subtracting 3 from 1. So I get minus 2d sine beta A. So that is 6. No, that is not the only thing that I can do. I can look at these equations. I can look at 2 and 4 and do the same thing. So if I add the two of them, I have alpha times A minus B e to the minus alpha A. Out here, I am adding the two of them, so the sign terms cancel, and I have 2d beta cos beta A. So that is equation 7. The last equation that I need comes by subtracting one from the other, and therefore I have alpha A plus B e to the minus alpha A. So I subtract 4 from 2 here. When I subtract, I have 2c beta sine beta A, and the d term goes. This is what I have. Now, given these 4 equations, let me start off by saying that A is not equal to B. Or let me start off by saying that A and B are non-zero. So which means these terms survive. So A minus B is not equal to 0. Now if indeed that is true, let me divide 7 by 6. If I did that, I get alpha is equal to minus beta cot beta A. So that is one thing that I have. So that is possible. I could have used this equation, and I could have divided equation 8 by equation 5, and that would have given me alpha is equal to beta tan beta A. So one solution is alpha is minus beta cot beta A. I got this by looking at these two equations. So 7 divided by 6, equation 7 divided by equation 6 gave me this. The other solution came because I divided equation 8 by equation 5, and that gave me, so this is one solution. The second solution for alpha is got by dividing equation 8 by equation 5, and that simply tells me that alpha is equal to beta tan beta A. So this came by dividing 8 by 5. Both solutions are there. We need to proceed and see what these solutions give us. So let me first consider the second solution. Alpha is equal to beta tan beta A. Right away, one thing is clear, that only certain values of beta A are allowed in this problem, because alpha is positive and beta is positive. So the tan function, only some values, some regions are allowed, and that I can easily check out now. So, tan beta A should be positive. I am considering the second solution. Since tan beta A should be positive, it is clear that 2s pi by 2 less than or equal to beta A less than or equal to 2s plus 1 pi by 2, where s can take values 0, 1, 2, 3, etc. So, if you now have beta A on this axis and this is the origin, and you have pi by 2 pi, 3 pi by 2, 2 pi, etc. on this axis, 0 to pi by 2 is an allowed region for tan beta A in this problem, but pi by 2 to pi is not. Then when s is 1, pi to 3 pi by 2 is allowed, and so on. So, there are only some regions which are allowed for beta A in this problem. So, we have to look at that. That aspect has to be looked at. Now, let us go back and use the fact that alpha A is dimensionless and beta A is dimensionless, and therefore, I can do the following thing. I can find out alpha squared plus beta squared A squared. Now, alpha squared plus beta squared A squared, you will recall, is 2me minus 2me by h cross squared plus 2me by h cross squared plus 2mv naught by h cross squared, and therefore, times A squared. So, this object is simply equal to 2m v naught A squared by h cross squared, but that is the same as v naught by delta, where delta was h cross squared by 2m A squared. So, here is a dimensionless quantity that is equal to another dimensionless quantity v naught by delta, which is the strength of the potential. So, that is the significance of alpha squared plus beta squared times A squared. So, let me substitute in this equation alpha is beta tan beta A. Now, if I did that, I have beta squared times secant squared beta A is equal to v naught by delta. That is what I have out here. There is a 1 by A squared. And therefore, this implies that secant squared beta A is v naught by delta 1 by beta A the whole squared. In other words, cos squared beta A is delta by v naught to the power of, okay, cos beta A is delta by v naught to the power of half times beta A. That is what I have for my equation. Let us look at this equation. This equation simply tells me the following: cos beta A, I chose alpha to be beta tan beta A. I chose that solution, and then I have cos beta A is delta by v naught to the half beta A times beta A. You see, this equation can be solved for beta. Beta is what has the energy in it. Beta is 2m E by h cross squared plus 2m v naught by h cross squared, and therefore, to solve for beta and see if the energy is quantized, the only way I can do it is by using some sort of graphical plot. So, I have beta A here, and as I have already argued, 0 to pi by 2 is an allowed region in this problem for beta A. Pi to 3 pi by 2 is an allowed region in this problem. So, these are the values that are allowed for beta A in this problem. I also know that this quantity is positive, delta is positive, v naught is positive, and beta and A are positive. So, indeed, I should be writing modulus of cos beta A is delta by v naught to the power of half beta A. So, I can plot the right hand side separately here. So, I plot delta by v naught to the power of half beta A versus beta A. That is going to be a straight line. So, basically I can choose various values of V naught by delta. So I get straight lines depending on the value of V naught by delta. For instance, if V naught by delta is shall we say 50, remember this is dimensionless, this could be the straight line, and if V naught by delta is less than that, let us say 20, this would be the line. If V naught by delta is 5, this could be the line, and so on. So I get various straight lines with different slopes. It's clear that the line passes through the origin, and that's an important point, which I will talk about a little later. So you have various straight lines depending upon the numerical value of V naught, in other words, depending upon the strength of the potential, how much bigger V naught is compared to delta. So what are the allowed solutions? Where cos beta A, let's take that to be 1, where cos beta A cuts these lines. So let me for reference keep just one line. And draw cos beta A. So cos beta A, this modulus of cos beta A is what we want. So it starts from 1 like that, and so on. So I am not drawing that part. Question is, where does this modulus of cos beta A cut that straight line? Certainly the origin is not a point, and that is an important matter, because certainly one solution for beta is there is certainly one cut, right? And here, now this is within the allowed region, this is a forbidden region, so this is not an allowed point, but this is an allowed region, so that is an allowed point. So you already see that beta is quantized, and since beta is quantized, the energy is quantized. So if you fix V naught by delta, so given the strength of the potential, it is clear that there are only some values of beta which are allowed, and since those are the values of beta that are allowed, the energy also is allowed only discrete values. Now I could have done the same thing using the first solution, alpha equals minus beta cot beta A. So you can repeat the argument. It is clear that one bound state is definitely allowed. See, one bound state is definitely allowed. This is an important point, because however shallow the well may be, however shallow the well may be, in other words, even if the well were not deep enough to hold several bound states, you are guaranteed that there is one bound state available in the square well problem. Now this is an important aspect, because you see, whenever I study bound state problems, I have to choose a model potential. Certainly sometime in the near future I will talk about the deuteron problem as an application of the square well potential. The deuteron is a bound state of the neutron and the proton. It is a very loosely bound state. There is exactly one state of energy which keeps it bound, for which energy is negative, and then even a small perturbation, a small kick, a small amount of energy given to the deuteron will separate the neutron from the proton, and the energy will no longer be negative. It won't be a bound state. So the square well is a very good potential to choose for the deuteron, because it allows for at least one bound state. I know the deuteron exists in nature, and I know it is a loosely bound state. So depending upon the shallowness of the well, you can arrange for a certain number of bound states to be there in the problem. Returning to the first solution, I will urge you to put that in. Alpha is minus cot beta A. If you did that, you would find that things do not change too much. You will have modulus of sine beta A is this quantity. It should be easy for you to see that. And once more, instead of modulus of cos beta A, which I have plotted here, you would plot modulus of sine beta A. You will discover that whatever I have said till now about at least one bound state being guaranteed holds good. So that is the story of the energy eigenvalues in this problem. Given beta, I can always go back and write out my energy. So E sub n can be written, because I know that 2m E sub n plus V naught by h cross squared is beta n now squared. So given this, given the values of beta, I can find out E sub n. Discrete energy values, corresponding to which we have to find the energy eigenfunctions, which is what I will take up in my next lecture.